Good evening, sir.
Good evening, sir.
Good evening, sir.
Yes, good evening, everyone.
Good evening, sir.
Good evening, people. Do you have any questions until hydrogen atom, people? We're continuing with hydrogen atom, but if you still have any questions until then, until what we covered in the last class, you can ask. Sorry. Okay, so let's continue. Okay. There we go. So let's continue with our chapter on quantum mechanics. That is, we have started with FCTQ since long, and we will complete this chapter, people. So we started with hydrogen atom in the last class, and we had started with series Lyman, Balmer, Paschen, bracket, and P5. Okay, so I will just directly write the formula. We had learned that 1 upon lambda was R into 1 upon N1 square minus 1 upon N2 square. However, this formula is correct for hydrogen atom. If you have hydrogen-like species, people, then you have to multiply this with Z square. Don't forget. I've written Z square maybe here wherever you write it. But if you have hydrogen-like species, if there is nucleus, if nucleus has a charge, if nucleus has protons, then you have to obviously ensure that you multiply this by Z square. That is the number of protons, or you can say atomic number. That is atomic number. You can also say number of protons. Okay. Now, a popular question is in exam that they ask: find the shortest possible wavelength or the longest possible wavelength emitted in Lyman series, or emitted in Balmer series, or emitted in Paschen. Or you can ask to find the ratio of shortest wavelength of Lyman to the shortest wavelength of bracket. Like shortest and longest wavelength. Around these questions revolve a lot, people. So let's understand that what exactly is this. Okay. Okay. So to start with, recalling a few things. Hang on. Okay. We have got n equals to 1, k shell, n equals to 2, n equals to 3, n equals to 4, n equals to 5. Okay. So when we talk about Lyman, tell me one thing. See, I will give you a shortcut trick to identify shortest wavelength. If wavelength is maximum, people, then energy is minimum because E is hc by lambda. How do you emit the wavelength? When a particle jumps from higher excited state to ground state, like second to first, or like third to first, or fourth to third, anything. Basically, when an excited level, higher excited level, falls to a lower state, people. If this happens, whatever is the loss of energy that is emitted in terms of radiation, and that radiation is some amount of wavelength. Okay. Energy is hc by lambda, or the emitted energy is h nu, or you write hc by lambda. So if energy is greater than lambda is smaller, no? If energy is smaller, then lambda is greater. So the best way to identify shortest or longest wavelength, you need to remember energy that you calculate delta E, which is E2 minus E1, which is actually h nu, which is hc by lambda. Okay. So larger the energy, people, smaller the wavelength, and smaller the energy, simple, larger the wavelength. Clear? Tell me one thing. If you talk about Lyman series, it means you have to end at n equals to 1. So this is one possible Lyman series, k alpha series. This is also Lyman series, k beta series. This is also Lyman, k gamma. This is also Lyman, k delta. And similarly, you can go on. Remember that at n equals to infinity, energy becomes 0. Don't forget that. Energy becomes 0 at n equals to infinity. Here energy is minus 13.6 z square. We have written these values in the last class. Okay. Here energy is minus 3.4 z square in electron volts. Absolutely. Okay. And then it goes on. Now tell me one thing. Where is energy transition happening maximum? In alpha, you are getting 3.4 to 13.6. It's around 10. Here you will have people how much? Here you will have larger transition, don't you think? Here I think the value was minus 1.51, right? Z square electron volt. Now, from here to here, see, all of these are Lyman. K alpha is 3.4 to 13.6. Smaller transition. 1.51 to 13.6. Larger transition. Here to here, larger. So, people, where is the smallest transition and where is the highest transition for Lyman series?
K alpha is the smallest, and K delta is the largest.
Beyond K delta, we can go. We can go
Yes,
this, whatever
infinity,
you want
from
to use.
infinity to.
So, you can say whatever K last, whatever you want to call it, whatever letter you want to use, it doesn't matter. Okay. So, you can call this K infinity if you want to call it whatever. So, the point is, people, in K alpha, energy transition is least, and in K infinity, whatever you want to call this, people, okay, or you can call this K max, anything, any notation is fine. Okay. So, suppose K infinity. In this transition, energy transition is maximum because we're going to 0 to minus 13.6. Huh? That's it. So, you can say K alpha has got minimum energy transition, and K infinity, if you want, you can call it, has got maximum energy transition. So, if you want to find shortest wavelength, where can you find shortest wavelength? Which transition will give you shortest wavelength? K infinity, no? Because we just learned energy is inversely proportional to wavelength. Here, if energy emission is maximum, then wavelength will be minimum. So this case will give you shortest wavelength. This case will give you shortest wavelength. And this case will give you longest wavelength of Lyman series. Longest wavelength of Lyman, shortest wavelength of Lyman. Okay, that's important. And now I think it's logical. So can I in the next way directly say, so shortest of Lyman as you just wrote, shortest of Lyman, you just wrote, it is which one, people? K infinity, it means infinity to 1, no? Infinity to 1. Don't you think what will be shortest of Balmer now? Infinity to 2. Shortest of Lyman, Balmer, Paschen. Obviously, now you know the trend of this. It will be infinity to 3, and you can have bracket, you can have P fund, you can have Humphrey. Okay, which is infinity to 4, infinity to 5, and infinity to 6. And similarly, longest wavelength of Lyman. This is shortest wavelength of Lyman. Okay? Longest wavelength of Lyman, as we just learned, it is K alpha initially, 2 to 1. That's it. K alpha, 2 to 1. So now we know the trend. Longest of Balmer, it has to be what, people? 3 to 2.
3 to 2.
Longest of Lyman, Balmer, Paschen. It will be 4 to 3. And it goes on. You can keep on writing this. I hope you understood this. Tell me if not. Just a second, what's happening? I have no idea why this has been happening, and only this happens in our class. Through the 6 hours, people, but it doesn't happen. Maybe I recommend that because I don't use open code for other lectures. Hang on, let me figure this out now once again. Things have hung up. Wait, let me try clicking on open code once again. Search. I lost a few things, but I think that's okay. Let me share the screen and check. Okay, copy this. You start from here first. Take your time, ask me if you have any doubts, and I think you have already copied this. Copy this, please. Tell me if you want to explain any part of this. Huh? Greater the energy transition, lesser the wavelength. Simple. Here, energy transition is least.
Done, sir.
Just a minute. It's automatically. I'm not able to click on pen. It is becoming rubber automatically here. I think I will just. Okay, I will copy this even. Copy this one better. So Balmer will be 3 to 2, and similarly Pastel, it will be 4 to 3. That is the shortest transition in Pastel. Now 4 to 3 will have least energy people. So maximum wavelength, simple. 5 to 3 will have greater energy, small wavelength. 6 to 3 will have even greater energy emission, even smaller wavelength. Okay. So shortest wavelength will be infinity to 3, and the highest possible wavelength will be 4 to 3. And then you can write for bracket P1 and half wave also. For bracket you will have 5 to 4, for P1 you will have 6 to 5, and for half wave you will have 7 to 6 people. Tell me if you have any questions, please. Clear, everyone?
Yes, sir.
Good. Chalo, next, proceed ahead. Let me write, okay? So suppose if I would write a question here, find the ratio of, I will just increase the level directly of this. We have been taking any easy problems. Find the ratio of shortest wavelength of Balmer series to the longest wavelength of P1 series for He plus atom. He plus. So you have to obviously first understand the energy also. Okay. What is the formula first of all for He plus? So the formula, if you remember, is minus 13.6 upon n square into z square. Okay. So this is minus 13.6 upon n square z. For helium, it is 2 people. Helium is 4He2. Okay. So this is AXZ. Z is 2 people per helium. Okay. So 2 square. So this is minus 13.6 upon n square into 4. So this is 13.6, 27.2, 54.4, minus 54.4 upon n square electron volts. This is En. First you copy this. En. Be honest if you have questions. Ask. And please practice papers, people, okay? Like you need to train yourself on how to sit, how to attend 3 hours at a stretch in an examination hall. Directly, if you're going to give JAM examination, then obviously that 3 hours continuous, you won't have a habit of it. So train yourself, order mock test papers online. Okay? There are good books available. Like you can find previous year's question papers or JAM mock test papers. You can order the books. You can keep a 3 hour timeline and just ensure that you practice enough, at least 5, 10 good mock test papers you can practice. Sit for 3 hours and give the papers. As many papers as you will give, greater your art of giving a paper will increase people. Okay. Having knowledge and solving questions in your room, in your comfort zone is a different thing. Solving it in an exam pressure when you have a time limit, that's a completely different thing. So practice is something you will require. Give some mock test papers.
Sure, sir.
Okay, done. Chalo, next. Proceeding ahead. So let's calculate. We want to first talk about shortest of Balmer. So how do we quickly understand this? Simple. Lyman, Balmer. So I have to end from 2 to 2. For Balmer, we will end it. So what are the possibilities? 3 to 2, 4 to 2, infinity to 2. Here transition is minimum, energy transition is minimum. Here energy transition is maximum. So when energy transition is minimum, lambda is longest. When energy transition is maximum, lambda is shortest. This is how I quickly understand it. I don't have to by heart that infinity is for shortest or this is for longest. That for me is very risky. So I take 10 seconds and I try to understand that what should be lambda shortest. That's it. So this will be lambda shortest people. So I have the formula 1 upon lambda is rz square. It is rz square into 1 upon n1 square minus 1 upon n2 square. By the way, so even though we calculated this, I mean, this is not required. We have already z square in the formula. Okay, but I mean, you could have used e2 minus e1 basically. I was planning to use e2 minus e1, just saying, like en2 minus en1 is xc by lambda. So if you use this formula, then you can go ahead with this. So you can calculate en2, you can calculate en1 respectively. Okay, and then you can use xc by lambda. But we already have a formula, right? Okay. Otherwise, you can use en2 minus en1. That's also fine, absolutely fine. So R, we know it is 1.093 into 10 raised to 7. Z square. Z is 2 square. That is 4. You are going from n2 to n1. Always remember. I want to work on shortest now. This is n2 to n1. Understand? So 1 upon n1 square. So that's 1 upon 2 square. 1 upon n2 square. That's 1 upon infinity square. Okay. So you have got 1.093 into 10 raised to 7 into 4. 1 upon 2 square is 1 by 4. Anything upon infinity is 0. 4 gets cancelled. So lambda is inverse of Rydberg's constant in this particular case. It is 1 upon 1.093 into 10 raised to 7. Actually, we can be a bit more smart here because it's a ratio problem.
Yes,
R will get cancelled. R and Z square will actually get cancelled. Correct. Okay, but okay, so we can do one thing. Because we have realized it, because it's a ratio problem, we can keep rz square as it is. Only because it's a ratio problem. So let's keep rz square as it is. This is 1 by 4. Okay. So what do we have? So lambda is 4 upon rz square. That's it. This is the first case, shortest of Balmer. Now we want longest of P1. Longest of P1. Okay. So how do I understand quickly, people?
6 to 5.
Okay, I will jump. But Lyman, Balmer, Pastel, bracket P1. So I have to end at 5.
Yes,
so combinations are 6 to 5, 7 to 5, infinity 5. Again, from here to here, I have a minimum energy. Because I have a minimum energy, it means I have got maximum wavelength. That's it. So I would directly say, so 1 upon lambda in this case, it is rz square into 1 upon n1 square. Remember n2 to n1. Okay? So 1 upon n1 square, 1 upon 5 square minus 1 upon n2 square, which is 6 square. So this is rz square into 1 upon 25 minus 1 upon 36. This is 1 upon lambda. So this is rz square into, okay, calculation you can now do. Whatever. Complete the calculation, take the ratio, that's the answer. So I hope you understood how to approach these shortest wavelengths and longest wavelength stuff. Remember, you will get 1 upon lambda, reverse it, that you get lambda, take ratio appropriately. Okay, obviously, we have a very large answer because you're talking about a P1 series people. So you have a larger problem. So that's okay. Clear, people? Shall we?
Yes, sir.
Shall we? Next, leave half a page for remaining calculations you want to do later. So that was one thing that I wanted to add in Haydn's atom. Now let me check. I've already told you that nth excited state means n plus 1th level. So take care of that also. Nth excited state would mean n plus 1 level, or you can say quantum number is n plus 1 degree. That is first excited level people, first excited state, that is second level, n is 2. Okay, so for n excited state, you can say the principal quantum number that you have is n plus 1 for hydrogen atom. This is my principal quantum number. There are types of quantum number which we'll eventually discuss also, but right now you can write for hydrogen atom, okay, for n excited state, principal quantum number is n plus 1. So like if I would give you third excited state, it means the value of n is 4, it's not 3. Value of n is 4 actually. Now suppose they give you an upper limit n2, like they can give you the maximum possible outermost orbit available in that particular atom. I think I spoke a long language of English. What I was saying is, suppose they would give you maximum outermost orbit. Let's say third is the outermost maximum possible outermost orbit. Fifth is the maximum outermost possible orbit. That is what they have given. And they are asking what are the possible number of transitions you can have, what are the possible number of series combinations you can get, how many kinds of discrete wavelengths, how many kind of radiations you can emit. Suppose that is the question. I hope you copied the statement right now.
Copy.
So suppose if n2 is fixed, okay, and they are asking you how many possible transitions. How many possible transitions? Okay, so let's understand. Why 2? N2 could be anything. No? So suppose I have got, I'm drawing these things. This is n equals to 1, this is n equals to 2, this is n equals to 3, this is n equals to 4. When you say n2 is any higher orbit, n2 to n1, when you jump from n2 to n1, so outermost possible orbit they have given. Suppose particle is here, let's say n2. N2 is 4, suppose. Now how many transitions are possible? So mathematically we can calculate. First of all, it can go from 4 to 1, that's one combination. Okay. Another combination is 4 to 2. Okay. Another combination is 4 to 3. Another combination is after it goes to 3 people, after it goes to 3, 3 to 1 is also possible, 3 to 2 is also possible. After it goes to 2, 2 to 1 is also possible. That's it. 4 to 3, 4 to 2, 4 to 1, 3 to 1, 3 to 2, 2 to 1. That's it. So how many combinations are there? People? 6. 6 possible discrete wavelengths you can get. Correct? 6 discrete wavelengths we can get. Okay. Copy this first. So maximum outermost orbit they have given. So these are the only possible transitions that can exist, right? Beyond this, we cannot have any other transitions. Discrete transitions. That is what so Neil Bohr's idea was about. You cannot have continuous emission of radiation. Whatever will be the radiation, it will be either of these 6. You cannot have anything beyond this now. You are doing basically probability structure, combination kind of stuff. Okay. So suppose if n2 is 2, how many transitions are possible?
So 1.
Only one.
Okay, only 1. Okay. Suppose n2 is 3, how many transitions are possible?
So 3.
3. Okay. So 3 to 1, 3 to 2, and 2 to 1. Okay. So you have got 3 possible transitions. 3 transitions. 3 to 1, 3 to 2, that's done. 2 to 1, that's it. Like basically it has gone from 3 to 2 and then it has again gone from 2 to 1. That's what. Okay. And we just learned if n2 is 4, we have got how many transitions? We just learned 6 transitions. Okay. Now there is a shortcut formula for all of them. Number of possible transitions. So by any chance, are you aware of this pattern formula? When you have 1, 3, 6, and then I think after this you probably have 10, I think so. You have seen this pattern somewhere, I'm sure. Are you aware of this formula 1, 3, 6, 10 pattern? Anyway, answer is I think so, n into n minus 1 by 2. We can check.
Yes,
We can check. Check this. So 2 into 2 minus 1 by 2, n is 2 now. I'm substituting 2. So what do we have? 2 gets cancelled, you're left with 1. Outstanding. Now n2 is 3. So 3 into 3 minus 1 by 2. So this is 3 into 2 by 2, 2 gets cancelled. You have a 3. Answer is 3. You have a 4. Okay, substitute. 4 into 4 minus 1 by 2. So this is 2 into 3. Answer is 6. Beautiful. Take a look. Time saving stuff.
So n here is the outermost
orbit. That's it. Maximum energy state that the electron can occupy. And is the maximum principal quantum number, maximum level that the electron can occupy. Outermost orbit. This is a very popular series, 1, 3, 6, and after this I think you have 10 as far as I remember. You can check out 5 into 5 minus 1 by 2. That's 5 into 4 by 2. Yes, that's 5 into 2, which is 10. 1, 3, 6, 10. Whenever you have 1, 3, 6, 10, remember it's 10 into n minus 1 by 2. These kind of series things, especially test and DIPAR people, they enjoy a lot to ask. DIPAR is already done. Now test picture. By the way, DIPAR has already sent you a response sheet. I did not tell you that before. I think 4 or 5 days ago probably. They have sent you a response sheet. So whatever answers you marked in the examination, people, that is mailed to you. You have to check your Gmail updates column. It may not be there in the primary section. You may have to check your updates column. In updates, you will find your response sheet. But they have not yet sent the answer key. And I think they will probably upload directly the. No, but there will be a time. There will be a period where a debate will be allowed. So they have to provide the answer keys because there has to be a debate in between. Anyway, there were a couple of questions which I told you were wrong in paper. So done, everyone. Next.
So JAM will also have a debate period.
Absolutely. There will be 4 5 days, and I will help you all to find all the English mistakes we can in the paper and increase as many marks as we can. Okay, so that's it. Just a second now. So we learned number of possible transitions, and similarly, they can also ask you the other way out, like number of possible excitations. Okay. So again, I can give let's say 3 levels. Okay.
n minus 1 over.
I'm not sure about the formula. I don't know if there is a general formula. So we can think about it. So suppose electron is present here. So how many excitations are possible? You can go from 1 to 2. It's the same formula, I think so. 1 to 2. I'm not sure. Then another possibility is 1 to 3, and another possibility is 2 to 3. So I think it should be the same formula because here also when n is 3, answer is 3, and then not sure. N is 3, answer is 3. You will have the same formula. Number of possible excitations. You can either go from 1 to 2. That is one possible excitation. Another excitation is 1 to directly 3. Another possible excitation is 2 to 3. Electron can go from 1 to 2 and then 2 to 3. Same formula. Same numbers. Number of possible excitations. So again, if they give you outermost orbit, suppose if they give you there are 3 orbits possible, number of excitations will be again n into n minus 1 by 2. Same formula. we can always check if I have 4, it's reverse only. No? So 1 to 2 I can go, 1 to 3 I can go, 1 to 4 I can go. If I'm going from 1 to 2, then 2 to 3 is also possible, 2 to 4 is also possible. If I'm going from 1 to 3, then 3 to 4 is also possible. Again, I'm getting 6 possible excitations. Same formula. So if you give 3 orbits, number of possible excitations will remain same. Great. Okay, so that's all about hydrogen atom people. And now we have to take the last topic of this chapter, that's group and phase velocity. To understand that, please give heading wave package. Okay. Now, first of all, I need you to understand that what is the current model of electron around the nucleus, current as far as the 21st century is concerned. We discussed about the first model people that electron is a C and atom is a C and electrons are floating on it. This was the first Plum pudding model. Then came the second model where you have nucleus in the center and electrons are revolving in orbits around it. Okay. Then came the third model where you have nucleus but electrons are moving in SPDF shell. You draw that SPDF which you learn in chemistry. Orbits, but it could be around any angle. Then you learn the dumbbell shape and that shape, whatever. That's the chemistry part, SPDF orbits. And then the current idea is there are no fixed orbits. We can never know the certainty. We can never tell the certainty that electron is always going to be present. Here, there is a cloud. There is a cloud. Basically, there is a probabilistic region within which electron can be present anywhere. We have no idea whatsoever about with accuracy. We can never say what is the position of electron. So this is known as electronic cloud. Cloud basically means it is a region within which electron could be present. We can say for sure that beyond this it is definitely not present. We can set an outer limit, but we can never know that where exactly inside the system is present. So now the current model is you have a nucleus, and around the nucleus there is an electronic cloud within which it could be present anywhere. People. And this is the diagram that you have seen probably in front of your science textbooks, people, the cover page. Okay. So the thing right now is that every atom, so every electron that you have, electrons are not fixed. They are not localized. This is a scientific word. We cannot localize an electron. Basically, we cannot say with certainty that this is the location of the electron. First, we write this, people. We cannot localize an electron. We cannot localize an electron. Basically, with certainty, we cannot say this is the position of the electron. However, we attach a wave to the electron. People. The best idea to understand electron is wave mechanics. We convert it into the quantum world. We use probabilistic theory. Okay? And we cannot say with certainty that this is the position of the electron, but we can say with certainty that this is the region within which electron is going to be present. So this is known as attaching an envelope to the electron. Like for example, what is an envelope? Envelope is something within which you keep a money. So you may not know what is the position of the coin inside that envelope. Suppose you have put a coin. Obviously, we can see like the technicality is there that you will see the reflection or whatever. But just saying, so suppose it's a very hard envelope, and you have no idea whatsoever what is the position of the coin. Coin could be present anywhere, but it is always inside the envelope at the end. So envelope can be localized. Similarly, you cannot localize an electron, but you can attach an envelope to it, which we call it as matter wave. We can attach a wave to the electron, and that wave will give me a region. That wave will give me a region within which the electron will be localized. However, you can say, we attach a wave function psi to the electron, which acts like an envelope, and we can at least say for sure that electron is in that envelope. Okay, so that is basically you can say electronic cloud. Now the thing is, mostly the envelope does not move. The cloud is fixed. But yes, there are cases, like for example, what if the medium changes or whatever, where the envelope can also start moving. Like even envelope is moving. So already there was a problem that electron was attached inside the nucleus. Now electron was moving randomly inside. Electron was inside the envelope and electron was moving randomly in the envelope. Now what if the envelope also moves? That's a very difficult case to understand. But actually, it's for an example, people, right now all of us are electrons. Assume all of us are electrons. We all are attached to the Earth. Earth is our envelope, you can say. So we may be randomly moving inside, but all of us are right now on Earth, and Earth is like an envelope for us. So it is atmosphere is like an envelope for us, and we all are inside it. But Earth is also moving, technically. Earth is also moving. Similarly, for Earth, solar system is the envelope. For solar system, Milky Way galaxy is the envelope. For Milky Way galaxy, the whole universe, our universe is the envelope. So the point is, the cloud that we speak about, if even that starts moving, that is the case when you say that this is a group velocity. The velocity of the envelope is known as the group velocity. We all may have individual particle velocity. Like I can have a different velocity, you can have a different velocity. All of us right now have different individual velocities, which is known as particle velocities, which is actually known as phase velocity in quantum mechanics. I will eventually need to understand why particle and phase are one and the same. If you want, you can write this temporarily. That particle is phase. Write it above margin. As far as I also remember. I'm also not 100% sure, by the way. You can just check it. But just make a note. Particle is phase. Just make it. Then we'll just go and put a question mark. We'll try to prove that. Particle is phase and just put a question mark there. Okay? Because all the particles can be given different phases now. All of us have different latitudes, people. All of us have different angles. So all of us can be given different phase. All of us have different phase velocity. But because all of us are within the atmosphere, so whatever is the velocity of the Earth, Earth is continuously moving with a speed of 32 kilometers per second. All of us are also moving with 32 kilometers per second. So group velocity of all of us is same, but the individual phase velocities may be different. Okay. So you can write the velocity of envelope is known as group velocity. First, I will copy this slide. I would have directly jumped on the mathematics of this. Mathematics is very easy. Group and phase velocity equation, if asked in exam, they're very scoring. Nothing to do in that. But physics is something which I want you to understand. So electrons are in some cloud. If because of any medium, understand electrons are what? They are inside the atom. Now, atom can be affected because of the medium. So if atom will be affected because of the medium, electrons will also be affected because of the medium. So because of the medium, if the position of the electron is affected, the position of the cloud can also be affected. That's the whole idea. So if the cloud is moving, you can say envelope is moving. You can say you have a group velocity now. So that is known as group velocity. Okay, velocity of the envelope. Velocity of envelope is known as group velocity. Group velocity. Okay, and you can say velocity of individual electrons inside the envelope. Okay, that is known as phase velocity. And I want us to confirm later whether phase and particle are same or not. In classical world, we will check that. Okay. Chalo, next, proceed ahead. Okay, so now we will start with the mathematics. I've tried to give you a small idea of the physics of it. Okay, now let's understand the mathematics. Okay, so I will directly jump on. Please give heading non-dispersive medium. Okay, so write the condition as of now. In non-dispersive medium, people, derivative of phase velocity with respect to wavelength becomes 0. What does that mean? Phase velocity is independent of wavelength. Independent of wavelength. Now listen, what did I just say? Usually, medium can affect the electrons. If medium is affecting the electrons, it means refractive index is affecting the electrons. Refractive index is related to wavelength, mu2 upon mu1 is lambda 1 upon lambda 2. So it means wavelength is affecting the electrons, people. But if the velocity of the particles, the phase velocity, like I said, the phase velocity, the individual velocities of the particle, if it is independent of the wavelength, it doesn't even care what is the wavelength. In that case, our individual velocity will not change, people. If again I repeat, and if our individual velocities are not changing, will the group velocity change? No. Technically, group velocity should also remain same. Okay, let's check first of this. So Vp is independent of wavelength. Other language, in many books also, right? Vp is independent of propagation constant. It's one and the same thing. Because wavelength can be written as 2 pi by lambda, so that's fine. Vp is independent of propagation constant. That's also one and the same. Because lambda is nothing 2 pi by k, or k is 2 pi by lambda. So if it is independent of lambda, it is independent of k. Okay. So let us just rewrite and re-understand the definition of Vp. So I can say that Vp is basically, like you said, phase velocity, which I said is velocity of the individual particle. But you are not understanding them as particle, you have attached a wave to them. So you can say velocity of individual wave attached to the particle. Individual wave corresponding to the particle. What is wave velocity, people? It is f lambda. I can write it is f lambda. So this becomes I can write fs. Can I write this as 2 pi f and can I write lambda upon 2 pi? I'll just multiply and divide by 2 pi. Anyway, it is cancelled. I'm getting f lambda, doesn't matter. Okay, so 2 pi by gets cancelled. I'm left with f lambda. So I can further say what is 2 pi of omega? And people, 2 pi by lambda is k. So can I say lambda upon 2 pi? That's 1 by k. That's the total. Okay, so lambda upon 2 pi, that's 1 by k. Or you can say that phase velocity is omega by k. Phase velocity is omega by k. Copy this. And you might for a second think, but so phase velocity is dependent on k. You just said that it is independent of k. No, it is still independent of k. I'm coming to that. Hang on. Okay. You might feel that Vp depends on k, but no, it doesn't depend on k. I'm coming to that. Hang on.
So I didn't get your notion that in dispersive medium, group velocity कैसे affect नहीं होती.
I'm coming to that also.
Okay.
So basically, you can imagine, suppose you have a cloud. Just imagine a cloud, like a balloon, and you have electrons inside it. Okay. Suppose electrons are expanding. Basically, suppose they start moving, but because they all are independent of wavelength, they all have constant speed inside the medium. All of them right now have constant speed, so they all will move equally in all the equal directions. It's like the whole packet will also move together. It's like you're blowing the balloon. The particles are flowing. All the particles are flowing with the same velocity right now. All of them are moving with the same velocity. It means the packet will also move with the same velocity. In fact, what happens in non-dispersive is whatever is the particle velocity, or whatever is the phase velocity, same is the group velocity. They are one and the same thing here. How exactly? Let's understand that. Hang on. So Vp is omega by k. Copy this quick. Let me explain this first. Vp is omega by k. So people, omega is actually Vp into k. And the thing is, it's actually something like this. Omega k, straight line passing through origin. Vp is constant, Vp is slow. Vp is not changing. As k increases, omega increases. As k decreases, omega decreases. Here, omega is proportional to k, such that Vp becomes slow. People, Vp is constant. It means particle velocity or phase velocity, whatever, phase velocity. I'm using the word phase. I want to confirm later whether it's particle or not. I'm not sure about it, like I said. Okay? So, phase velocity that we attach to individual electrons is constant for each of them in a non-dispersive medium. In a non-dispersive medium, all of them have same phase velocity. People, all particles have same phase velocity. In non-dispersive medium, it's constant. Non-dispersive medium. So the crux right now we need to remember is in non-dispersive, omega is proportional to k, such that Vp is constant, and because Vp is constant, derivative of Vp with respect to lambda becomes 0. This is basically the summary right now, as of now, for non-dispersive medium. The slope here y equals to mx now. This is y, this is m, this is x. The slope here is Vp. The slope here is Vp. This happens in a non-dispersive medium. That's why I call it non-dispersive. It means dispersion is not happening, people. If dispersion is not happening, it means all the, suppose if you compare this with light, because electrons are behaving as waves, okay? So compare this with light. That's the best way to maybe understand this right now. So when a white light travels in a non-dispersive medium, dispersion is not going to happen. It means white light will remain white light. All the colors have same velocity. All of them have got same wavelength. All of them have got same response to the refractive index. That's it. But if dispersive medium is there, then what happens? That white light will split itself into the 7 colors with pure. If dispersion is going to happen, it means now all of them have got different wavelength. Because you have got violet, you have got indigo, you have got the pure people. Now all of them have got different wavelength. Now all of them have different phase velocity. Now it cannot be constant anymore. So in non-dispersive medium, this is 0. In dispersive medium, this is a function of wavelength, people. Different wavelength, different velocity, and hence you have got deviation. The best way to understand. You can also make a note that in dispersive medium, what happens is dVp by d lambda is not 0. Vp will be a function, people, of lambda. Or you can say Vp is also a function of k, whatever. Okay. Best way to compare, to understand this. Dispersion means what? Splitting of white light into its components, people. Okay. So if it is going to split, what does that mean? Now, initially, all of them had same wavelength, people, all of them had same velocity. All the colors were traveling together as white. But now, all of a sudden, all of them have a different wavelength. They split it and separated into components, different wavelengths, different speed, different refractive index. Everything is different for them. And by the way, I'm not sure. I hope you're aware of the fact that the refractive index that you guys study of material, for example, glass is 1.5 or water is 1.33. It's not constant.
Yes, it depends on medium.
No.
Two medium.
No. I mean, it depends on medium. That's fine. That is obvious. I mean, I said glass 1.5 and water 1.33. But it depends on light and dark. 1.5, which you say for glass, it is in response to the mean color of light. 1.5 refractive index, that is in response to yellow color. refractive index of the material. Remember, at atomic level, a lot of things is happening. Light enters, it interacts with electrons, everything it disturbs. Our refractive index changes people. So mu, which is 1.5 of glass, it is in response to the yellow color, which is the mean color of it. For violet color, you have a different refractive index. For red color, you have a different refractive index. For yellow color, you have a different refractive index. For all the colors, you have different refractive index. Hence, you see now, mu2 upon mu1 is lambda 1 upon lambda. What is the meaning of that? Different wavelengths, different refractive indexes of the same material. Material refractive index depends on the property of the material. At the same time, it depends on which light is interacting with you. Because depending upon light, the property, the nature of the material changes. It's a very rare idea. I mean, it's a very rare knowledge. Not many people have this, to be honest. But you have been using this. You have learned this without realizing it. I know in your 11th, 12th standard textbooks, you have got those problems where they give you violet wavelength and red wavelength. They give you violet refractive index as to red refractive index. You take the ratio, you calculate, but you have never understood probably what it is.
Yes, sir. There is, in the Snell's law, there is also there for a certain wavelength of light, and for a certain,
Yes.
the term was there.
Yes. Okay. So it is light dependent. Okay. So basically, if the, and this is only for dispersive medium. There are mediums that are non-dispersive. So for them, refractive index will forever remain constant. So there is no worry people there. But especially for dispersive medium, where the splitting of light is possible, it means that they behave differently in presence of different light. So all the particles will have different velocity, all the particles will have different wavelength, and the material will have different refractive index in response to the different wavelengths. Okay. Next. Proceeding right. I hope you have copied this. Next. So that was about dispersive. Now I want us to note this thing. What you said? Group velocity. So when will the group velocity exist first of all? Like I said, people initially that wait, hang on. So I just want you to note right now. Just make a note. Group velocity is derivative of omega with respect to k. So only if omega is a function of k, only if omega is a function of k, group velocity can exist. K or lambda, group velocity can exist. Group velocity means the envelope will move. Okay. So if the angular velocity, which is related to frequency, if frequency will change with wavelength, then all the particles will have different individual velocities, because of which the envelope will also start moving deeper, and the group will have some velocity. I will repeat the chain, listen to this. Omega is related to frequency, 2 pi. K is related to wavelength, 2 pi by lambda. When you say omega is a function of frequency, omega is a function of k, it's like saying frequency is a function of wavelength. If wavelength will change, frequency will change. If this is happening, which happens in medium, if that happens, it means all the particles, dispersion is possible. And if dispersion is possible because all of them will have different wavelengths, it means all the particles will move differently. It means now the envelope will also move differently, and you will end up having some group velocity. Now hang on, let's understand this further. So VZ, let's understand this for non-dispersive medium. Okay, first you copy this. Done, clear? Next. So if at all there has been too much of information right now which you are unable to process at the moment, which is perfectly normal, people, because it may be a very new concept to you. In that case, now give it a fresh start right now. Okay, let's talk about non-dispersive medium. So what you need to remember, the crux of what we just learned is that in non-dispersive, omega is proportional to k, such that Vp is constant. It means derivative of Vp upon lambda is 0. Next, the definition of Vg is general definition. Definition of Vg is what, people? Vg is d omega by dt. Next, let's calculate the relationship between Vg and Vp. Let's calculate. Substitute omega is dt by k here. What do we get? So Vg is dt by dk of. What do we expect in non-dispersive? All the particles are moving with same velocity. The group will also move with same velocity. It's like you are stretching a balloon, people, doing a balloon like I said. Okay. So the whole balloon flows with the same velocity with which the gas is expanding inside of it. Okay. d by dk of what do we have? Omega. What is omega, people? Vp into k. But Vp is not a function of k. Vp is constant, people. Vp is not a function of k. So Vp outside. What do you have? d by dk of k. What is derivative of k with respect to k1 now? Vg and Vp are same. Like I said, the envelope will move with the particles, people. Group velocity and phase velocity are same, but this happens only in non-dispersive medium. So in non-dispersive medium, Vg and Vp are same. Because Vp is not a function of k, Vp is not a function of wavelength, Vp is constant. dVp by d lambda is 0, dVp by dk is 0, it's not a function of either of them. Vp is constant, people. At the end, when you revise, you can directly jump from this. You can ignore the above theory. I try to explain the physics. If it is heavy, start from the mathematics directly. Because numericals on this are very easy, very easy. Okay. So start from this. Next, shall we?
Yes, sir.
Let's talk about dispersive medium. Dispersive medium. So in dispersive medium, like we said, that now Vp will be a function of wavelength. Now Vp will be a function of k. So now we can say that dVp by dk cannot be 0. Now we can say that dVp by d lambda cannot be 0. Okay. What is the definition of Vg? Vg is d omega by dk. Okay. So this will be d by dk of what is omega? Omega is Vp into k. Vp into k. Okay. But now Vp is not constant. Now Vp is a function of k2. Now Vp is not constant. Okay. So you can split this. What do we do, people? We will apply UV rule now. First constant derivative of second, second constant derivative of first. Let's do that. So what is Vg, people? Vp constant derivative of k with respect to k plus k constant derivative of Vp with respect to k. What do we have? Vg is derivative of k with respect to k is 1. Vp plus k into derivative of Vp with respect to k. This is a general formula. Dispersive or non-dispersive doesn't matter. A general formula, simple. Because tell me, if it is non-dispersive, anyway this becomes 0 now. You're getting your relationship back. For non-dispersive, Vp is anyway not a function of k. But if Vp is a function of k, you have a general formula. Simple. So now group and phase are not same. As you can clearly see, people, now group and phase are not same because the particles have got different velocities. Envelope will move differently. Clear, everyone? Please ask me if you have any questions. Don't hesitate. If you are thinking, so how will it be function of k? Like what kind of a function? It could be anything. E raised to k, sine k, k square, x, k cube, k x square. I'm sorry, 2k square plus 3 log k. Basically, it will be a function of k, any function, whatever they want to give an example. Clear, people? Shall we? Okay, next. So what kind of questions are expected in exam now? So suppose they have given you that in a non-dispersive medium, suppose they have given that Vp is directly proportional to Kq. Let me check now. Vp is directly proportional to Kq, and they're asking you find the relationship between Vg and Vp. Okay, that's the question. Case propagation constant. Okay. Okay, let's work on this. So by the way, listen, suppose it's an MSQ also. They have mentioned that Vp is proportional to Kq, and there are four options. One of the options is the medium is dispersive, one of the options is the medium is non-dispersive. Obviously, because Vp is a function of K, you will mark medium is non-dispersive. It's a function of K. Simple. Okay. So, pardon? Pardon? I did not hear.
Sir, dispersive में 1 से propose.
Sorry. Absolutely. Yes. Sorry. Yes. Okay. So in a dispersive medium, Vp is proportional to Kq. Find relationship between Vg and Vp. Absolutely. Okay. So what do we have? Suppose the formula is Vg is d omega by dk. So this is d by dk of omega, which is, you can say, let's say, that this is Vp is some constant c Kq. Whatever is c, we don't care. Okay. We'll have to get rid of c by the way eventually. C is not something they have here. So you have to get rid of c. So as of now, let's write this as omega. What is omega by the way? Omega is Vp into k. Vp is omega by k. No? Vp is omega by k. So Vp into k is omega. Just that Vp is also a function of k. That's the difference people decide. Difference is Vp is also a function of k. Okay. So we can say this is Vp constant derivative of k with respect to k plus k constant derivative of Vp with respect to k. Basically, you can directly use the general formula if you have by hearted that already. I have personally never by hearted it. So I take 10 seconds to come up to that step. Copy this. This definition is always valid. The difference is that in non-dispersive Vp is constant in the definition. In dispersive Vp is not constant in the definition. That is only the difference. I repeat, this definition is always valid. Vp is omega by k. This is always valid. The difference is only that in non-dispersive Vp becomes constant, and in dispersive Vp is not constant. Sorry. Hang on. I lost it all again. Okay. So anyway, whatever I wrote before. So Vp is ck cube, and we have got Vg. So you can directly jump on the relationship if you have a hearted. So what was the relationship? K plus Vp plus k into dVp by dk. You can directly use this. Okay. So what is Vp? Ck cube plus k into d by dk of Vp. What is Vp? Ck cube. Okay. So what do we have? We have Vg, which is equal to ck cube plus k outside, c outside. What is derivative of k cube with respect to k? 3k square. So you have got ck cube plus 3ck cube. You have got 4ck cube. But c is something which they will not give an example. You have to get rid of c. So what is c? C is Vp upon k cube. Have a look. C is Vp upon k cube. So 4 Vp upon k cube. 4 Vp upon k cube into k cube. So Vg is 4 times Vp. Make a note. Vg is 4 times Vp. Ask me if you have any questions. Do not hesitate. Listen, I could have also created this in an entity form. Like in an entity, I would have given that Vg is n times Vp, where the value of n is. Where the value of n is. And answer is what? Actually, say, could this be generalized here? Hang on. If this could be generalized, then that could be so outstanding. Can we check that? Like I have got 3 and I've got 4. What if it's 4 and 5 and 5 and 6, something like that is happening or not? Let's check. Let's take a general example. Suppose let's make it 10. See if you're getting this one or not. Let's do this. Wow. Okay. Interesting to check. Have you copied this?
Yes, sir.
Okay. Let's check this. Vp is suppose k raised to n. So Vp is some constant c into k raised to n. Okay. Vg is Vp plus k into dVp by dk. So this is, remember, Vg is d omega by dk. Don't forget this definition. So Vp, which is ck raised to n, plus k into Vp, which is ck raised to n. So Vg will be equal to ck raised to n plus k into c. I'm going outside. Derivative of k raised to n into k raised to n minus 1.
n plus 1
क्या बात करते हो? So this is, we have got c into, this is k raised to 1 now. So let's do this. Multiply them. Hang on. Let me erase this. Where is this eraser? So I have got c. I have got n. K raised to 1, k raised to n minus 1. So that's k raised to 1 plus n minus 1. Okay. So I have got c k raised to n plus c n. 1 minus 1 gets cancelled. C n k raised to n. Okay. I can take c k raised to n common. I'm left with 1 plus n. Who is c k raised to n? Outstanding. Wait. Okay. In exam, by any chance, if they give you this problem, that Vp is proportional to k raised to 7, you are going to save your 2-3 minutes, people.
Answer will be 8.
Answer will be 8. Okay. You will save your 2-3 minutes easily. Outstanding. Nice. Tell me if you have any questions, please. Don't hesitate. Okay. Actually, let me find a problem related to this that is already asked in exam. So maybe a bit different kind of a problem. Hang on. I have a sheet. This is modern physics, no? Group and phase velocity. Okay. Group and phase. Give me a second. Okay. So let me see. There are some questions here. Not okay. We learned this topic in oscillation. Have you learned this topic already in oscillation? Just asking.
No, sir.
Okay.
Not yet. Group and phase.
Okay,
Okay,
same topic, है ना? मतलब it's a replication.
Application completely. Because this is related to reflective index, right? So yes.
Okay.
Next. So jump 2017 question. See, it's a 2017 question. I don't know how difficult this will be. But okay. You know the story of 2017. So the question is omega square is given by, you can try this. Omega square is given by c square k square plus omega square p. The dispersion. By the way, listen. This is known as dispersion relation. This is not this. Relationship between omega and k is known as dispersion relation. Please write this. An equation showing the relationship between omega and k is known as dispersion relation. A relation showing, or an equation showing relationship between omega and k is known as dispersion relation. is known as dispersion relation. So right now this is the dispersion relation, okay? And they've given us C and omega p are constants. C and omega p are constants. And the question is, so this is for plasma, by the way. This is the relationship of omega and k for a plasma. In this plasma, the question is group velocity is, and there are four options. It is proportional to but not equal to phase velocity, inversely proportional to phase, equal to phase, or a constant. The first option is it is proportional to phase but not equal to phase. Okay. Second option is inversely proportional to phase. Third option is equal to phase, and fourth option is constant. Group velocity. Okay. Yes. Okay. Interesting. Let's solve this now. So what do we have? Vg, which is d omega by dk. Okay. So this is d by dk of omega, which is c square k square plus omega square p. Okay. No. Under root of this. Under root of this. Yes. Because this is omega square actually. So omega will be under root of c square k square plus omega square p. Omega p square, whatever. It's constant anyway. So derivative of root x is 1/2 root x. Okay. And then you have to redifferentiate the bracket. So if I redifferentiate this, c square is constant, derivative of k square is 2k, omega p is constant. Okay. Listen, c square is constant, they have mentioned, derivative of k square is 2k, omega p is constant, they have mentioned, derivative of
So what
constant is
is
0.
omega p?
Constant, they have mentioned, constant. Unnecessarily omega p. They can write alpha, beta, gamma. They want to
Yes,
write
sir.
omega p. Okay. I hate 2017 paper. But okay. So 2 gets cancelled. We have got c square k, we have got c square k upon under root of this. But what is this under root guy? It's again omega.
Omega.
Okay. So this is c
Inversely
square
proportional to
upon
omega.
omega k. Omega by k is phase velocity. So this is c square upon vp. Inversely proportional. Answer should be option. What do we have? 2. Option B. Let me check 2017 now. Yay. 2 marks. Got it, people. I don't know if I got this in my 2017 paper or not. I'm still not sure. We can anyway check this, but let's not waste time. Okay. Clear? Nice.
Yes.
Please tell me if you have any questions. Don't hesitate. I hope you understood what we did here. At few k below omega by k is vp. So it's inversely proportional to vp. Nice. Proceeding ahead. Let me know if you're writing, please. Has there been any professor who has done this in the class K after getting a problem solved? And am I the only one who gets this one excited?
No.
Till now, not yet.
Okay.
Only you and only.
So I'm just scared basically. Proceeding ahead. But I enjoy. Okay. Next. The amount of satisfaction that we get, obviously, I express it, nothing else. Also, so again, just like I taught you in quantum, in those expressions of Rayleigh gene, in expression of what were the names? After Planck. In those relationships, we had relationship in terms of lambda. I taught you can convert this into k, you can convert this into omega. Those relationships that we had. I think u lambda, d lambda, how to convert this into uk, dk, how to convert this into u, same can happen here also. Okay, I've given you a relationship of group velocity, which is d omega by dk, which we derived it as vp plus k into dvp by dk. Now listen, let me calm down. This is in terms of k. You can convert this in terms of lambda, and they can ask you which of the following is the correct expression. You can convert this in terms of frequency. They can ask you which of the following is correct expression. Omega, nu bar, anything that is possible here. So let's try at least one of them. Which one do you want me to try? Frequency, wave number,
Frequency.
Chalo,
It's indirect now.
inversely proportional. So yes, more difficult comparatively. So C is f lambda, C upon f is lambda. Okay. So and that's indirect also. Right, I just got your point. So lambda is this. So first I need to convert this into let's find the relationship between k and f. K is 2 pi by lambda. So 2 pi upon c by f. So now I got the direct relationship. 2 pi by c. I hope first understood what I did. I want to convert this into frequency format. Like I want to find how Vg varies as a function of frequency. I want to find this. Okay. So I have to find first relationship between k and frequency. K is 2 pi by lambda, c is f lambda, c upon f is lambda. So 2 pi upon c by f, 2 pi by c. Okay, good. Now, that's it then. No? Okay, k is 2 pi by c. What about dk? Dk will be 2 pi by c into df. C is constant. No? 2 pi by c into df. Substitute. What do we have? Vg is vp plus k. What is k? 2 pi by c into dvp upon what is dk? 2 pi by c into df. Oh, 2 pi by c, 2 pi by c gets cancelled. This is a very easy relationship. So Vg is just vp plus dvp by df. People. Plus dvp by df. I hope you understood this. This is how Vg depends with frequency. Take a note. Ask me if you have any questions.
So k is 2 pi by c, no? Where is f?
There is a missing F.
So f is missing.
F is missing.
Okay.
2 pi is the
I said 2 pi f by k. There is an f. Okay. That's absolutely. Add this. No? Okay, I will say this again. I made the mistake purposely. I wanted to see who notices.
Yes, sir.
Okay. Clear, people? Similarly, you can work on. ठीक है.
Yes, sir.
Yes, sir.
Okay, next. Now, also, we have got Vg, which is d omega by dk, and we have got Vp, which is omega by k. Vp may be constant, may not be constant, depending upon the kind of medium that you already know. Okay, people, what is energy? Energy is hv for a photon, and I can say this is hc by lambda. Okay, I'm going to write this as, or no, wait, let's keep it. I'm thinking something.
So what you are going to do?
That's a good question. So what I want is to find a relationship. I want to express energy, like a group velocity, as a function of energy and momentum. As a function of energy and momentum. Okay, and phase velocity also. Phase velocity also as a function of energy and momentum. Right now, what do we have, people? Right now, we have it in terms of omega and k. I want to bring energy and momentum to the picture. Okay. Keep asking me questions. Many times I may keep explaining things, but I may not have conveyed the idea. I want to share this. So I recently saw this movie, the 83 World Cup movie. So in that, actually, something like that happens. That Kapil Dev sets a field. Okay, and he tells the bowler that I set the field there, and there. Bowl, okay, like do the bowling accordingly. So the bowler asks, "Sir, where, when, and where?" I mean, I'm going to tell you right, so there, and there. But obviously, you need to explain where and when. So ask me. That's what are you trying to do? Okay. So E is h nu. I want to get rid of omega. I want to get rid of k. Okay. So how can I bring k into the picture, or how can I bring omega into the picture? I can now. What is
Lambda.
what is omega? 2 pi r. Omega is 2 pi r. Or 2 pi nu, whatever. Okay. So we can just do one thing. We can multiply and divide by 2 pi. Best. What is h upon 2 pi? H cut and there is nu also. Listen, what I did. Energy is h nu. I just multiply and divide by 2 pi. It's fine. I'll still get h nu. What is h upon 2 pi? H cut. What is 2 pi nu? Omega. So E is h cut omega. Clear? Next. Okay. Similarly, let's talk about momentum. Momentum is h by lambda. Multiply and divide by 2 pi. So I can say h upon 2 pi into 2 pi upon lambda is one and the same thing because 2 pi gets cancelled. I'm getting h by lambda. Okay. But what is h upon 2 pi? H cut. What is 2 pi by lambda? K. P is h cut k. You may have learned these relationships in college, not sure. Energy is h cut omega. P is h cut k. Substitute. So what is Vg? Vg is d omega by dk now. Multiply and divide by h cut now. H cut is constant. I can do that. I have no problem. I hope it's fine. Oh, sorry, h cut k. I just multiply and divide by h cut. People it anyway get cancelled. Doesn't matter. But what is h cut omega? Energy. And what is h cut k? Momentum. So group velocity is can also be expressed as energy as a function of momentum. dE by dt. Similarly, phase velocity. Don't you think it should be e by p? If this is d by dt, we can check. dP is omega by k. Multiply and divide by h cut omega. H cut k. What is h cut e? What is kp? So phase velocity is d by p. Start from here. Copy. Ask if you have any doubts. Don't hesitate. But this was funny. So what are you trying to do? Keep asking me, okay? I hope you understood this. Tell me if not.
Done, sir.
Okay. Others also let me know if anybody is writing. Okay. Copy this.
So in a single sentence, if we want to know that what is the definition of phase velocity and group velocity, what do you say?
Phase velocity is the individual velocity of the electrons inside, which is basically floating around the nucleus. But when you say phase velocity, it is not the velocity of the electrons. Like I said, I put a question mark. I'm not sure whether it's particle or not that we want to check. However, it is the velocity of the wave attached to it, like the wave nature of it.
Okay.
Because it's omega by k. Omega is what 2 pi by lambda. K is what k is 2 pi by lambda. Omega is 2 pi. Frequency and wavelength. These are not classical world properties. These are wave mechanics properties. So actually, it is wave velocity. It's not particle. I'm more clear now. Phase velocity is not particle velocity. People cancel that. I think I put a question mark. Cut it out, please. Right? It's wave velocity. It's not particle velocity. Phase velocity is wave velocity. Is wave velocity. Because you write omega by k, and omega is a wave property. K is a wave property. Omega is 2 pi f. K is 2 pi by lambda. 2 pi gets cancelled. You get f lambda. This is wave velocity. This is not particle velocity. Absolutely. So wherever you wrote, we put a question mark. Correct that, please. Phase velocity is not particle. Phase is wave nature attached to that particle. Wave nature attached to that electron. That's the wave velocity of that electron. Okay. And group, you understood that there are so many electrons attached in the cloud. If the cloud also moves, that's good. Clear?
Yes, sir.
And please correct this now. Phase is not particle. Phase is wave. Now let's talk about classical world. Somebody wants to ask something? Classical world. So people in classical world, what is kinetic energy? Half mv squared. I want to write this in terms of momentum. So what do we do? I hope you remember. M square v square upon n. Okay. What is mass into velocity momentum? So this is momentum square. Mass into velocity is momentum. M square v square is momentum square. So this is p square upon 2m. Okay. Now suppose okay, particle exists and particle has a constant potential energy. Potential energy is there. This is constant right now of the particle wherever you are. Okay. Basically, okay. Suppose you want to calculate this thing. Group velocity. What is group velocity? dE by dP. If I apply this, what happens? d by dP of energy. What is energy? P square upon 2 plus. This is total energy. This time. E is total energy. No? Total energy. Now what is total energy, people? Kinetic plus potential. What is kinetic? P square upon 2m. What is potential? You can write V. Suppose potential is V. Okay. Let's calculate group velocity. So group velocity is dE by dP. This is d by dP of P square upon 2m plus V. I hope you are with me. Tell me if not. 1 upon 2m is constant. What is the derivative of P square with respect to P? 2P. Potential energy is constant. What is the derivative of a constant? 0. 2 gets cancelled. P by m. What is P by m?
V.
Momentum per unit mass. Velocity. V. Group velocity is actually the particle velocity. Okay, it's not phase. V is, what is this? This V is particle velocity. Mass into velocity. This is particle velocity for the people. So group velocity is particle velocity. Nice. Group velocity is particle velocity. In classical world. Oh. This makes now so much more sense. Because technically, when we are moving, nice. People in classical world means to us now. So all the electrons inside our body, they have a phase velocity, individual phase velocity. We have the envelope of our electrons. We have the group of our electrons. So when you say I am moving, that's my velocity, particles velocity. So that's the group velocity of my electrons. Huh? I hope you understand this. Tell me if not. We are a body. We have electrons inside us. Those electrons have got phase people, individual phase velocity. We don't care about it. Okay. So I am the envelope of my electrons. So I am the group of my electrons. So whatever is my velocity, that's basically the group velocity. That's the group velocity. Outstanding. So in classical world, group and phase are group and particle are same. Nice. In classical world, group and particle are same people. Clear, everyone? Okay. So with this, we complete our chapter people of from classical to quantum successfully. Nicely. Very scoring chapter. Photoelectric effect, Compton effect, group phase velocity, and everything. Many questions will be asked from this particular chapter. Tomorrow is a very important lecture. Tomorrow we'll be starting with MFQM, mathematics required for quantum physics. MFQM, mathematics for quantum. Whatever we are going to study forward, tomorrow's lecture we are going to build the language of it, the ABCD of quantum physics. Okay? You may leave people. Thank you so much.
Thank you so much.
Thank you, sir.
Thank you so much to you, sir.
Thank you, sir.
No problem.
Thank you, sir.
Thank you, sir.
No problem.
So can you go to the second slide?
Second slide. Okay. So this is the first, I think so. This one,
No, the next one.
this.
1 minute, sir. Non-dispersive medium.
Acha, for that
That's
particular
topic
topic. Acha, for that topic. Okay, this.
Okay, sir. Thank you.
No problem. So let me send it. Thank you.